Thank you really a lot to Laura and Victoria for inviting me here. It's great. I'm going to present you something which I've never presented before, so I hope the presentation is well timed. And I'm especially excited to present it in front of you, who I think are the right audience. Before I start, I need to thank all the people that collaborated in this work. Most of the experiments were done by Clotilde and Bagianat. Clotilde developed the system, and Bagianat further explored it. The theoretical part has been done in collaboration with Sudipta, who sent me this weird selfie, and Jean-François Genip, and of course the whole group and my supervisors, Manuel Thierry and Laurent Blanchouin. You might ask, what did I actually do? And I will not answer this question. And this will soon be submitted, so you find it soon. I want to start with a Vienna special, particles in a box. Two kind of particles, pink and blue, cyan and magenta if you're particular. Nothing happens, they mix and nothing interesting happens. And now I don't have the authority to cite the Bible like Roberto did, but I can cite one of the prophets, Maxwell, who at some point came up with the idea of, let's put inside this box some kind of agent, which he called a demon, who is able to read the state, the microscopic state of the particle, and act on them. Of course, the original Maxwell demon is not what I'm going to tell you about, but the similarity here is that this demon has a magic tail, who, when in contact with a magenta particle, it will push it right, and when in contact with a blue particle, it will push it left. And very fast, the system evolves into a new steady state where there is an excess of magenta particles on the right and an excess of cyan particle on the left, until the diffusive flux of particles that are trying to escape, I will be very not precise with the notation, compensate the pumping activity of this demon. Again, we now know this needs energy. It's not really what Maxwell had in mind, but the big intuition here is that if we can read microscopically the state of the particle and act on them, interesting thing can happen. Now, this problem of segregating particle is important in biology. So what you see here is a cell, and cells have a center and a periphery, and they might want to bring some proteins to the periphery and some proteins to the center because that's where they need them. So somehow they had to come up with their own version of the Maxwell demon, and one of the solutions they found is cytoskeletal transport. So what you see here, it's a network of filaments inside the cell called the cytoskeleton. Specifically, these are microtubules. And these are not simply filaments, they're polar filaments. They have a directionality, and they are organized spatially sort of this way, so they go from the center to the periphery. And there's another set of proteins called molecular motors that can literally walk on these filaments along their polarity and transport cargos. And not only do we have proteins that walk along the polarity, there's also proteins that work, motors that work in the opposite polarity. So when they transport a cargo, this one, of course, the magenta one will start from the center and going to the periphery, this one vice versa. So somehow this configuration is a bit the Maxwell demon I was telling you about. You start with isotropically distributed particles, whatever they are, nutrients, proteins, and you end up with particles at the center or the periphery where the cell actually needs it. And the question today is whether we can build this using purified components. More specifically, in the lab, we purify filaments, microtubules, actin, whatever you want. We purify molecular motors. We mix them together and cross our fingers and hope we get a cell. You'll see, we get something that looks a little bit like this. The main system that has been used to study cytoskeletal organization is the gliding assay. You have seen a bit of something like this in the previous days, where basically you take your motors, you stick them to a surface so they cannot move. You put the filaments on top. The motors will try to walk on the filament, but because they're stuck, they actually push the filament in the opposite direction, and you end up with gliding filaments on the surface. And this system has been shown, if you increase the density of filaments a lot, to organize into polarized states. So you get both polar density waves pneumatic bands. You can get a very rich kind of phases. But if we want to study cytoskeletal transport, we have two issues. One is that the motors are not moving, they are stuck on the glass. And the second one is that the network is moving around, it's not contained inside a cell. So to solve the first problem, recently, people have developed a slightly different kind of gliding assay, where now the motors are not bound to a solid substrate, but to a fluid one, specifically a supported lipid bilayer, so a lipid membrane. Now, the motors are diffusing on the membrane, but there is enough drag in the membrane to still push the filament. So what's going on when in this movie that I show you is that the filaments are still moving slower because part of the force is going into walking on the membrane, but the motors underneath these filaments are moving in the opposite direction. And again, raise the density, you get slightly different but still collective phases of gliding filaments, again with their own polarity or nematic order, but still the motors now are moving, but the network is going everywhere. And as intuition, what you can do if you want to localize your network is that instead of having only one motor going and pushing the filament in the opposite direction, you can add a second motor that will go in the opposite direction and then push in the opposite direction, and you hope that this will sort of stabilize your system. So the system I'm going to describe you is composed like this. You have a glass cover slip on top of which you have a lipid bilayer. You have motors of two kinds stuck on the lipid bilayer, and they are diffusing around on the membrane. Every now and then they hit a filament and then they walk. Each will walk in its own direction. And while walking on the filament, they will push the filament in the opposite direction. So this is the important part. The motors walk on the filament and push the filament in the opposite direction. There have been experiments like this where two kinds of motor were mixed together, but the results are somewhat boring. I mean, if you put too much of the motor that goes in the positive direction, you get positive motion. If you put too much of the motor that goes in negative direction, you get negative motion. And if you mix them in the right concentration, you have a tug-of-war situation where none of the motor is winning and the filament just doesn't move. Now we're going to do the same on a fluid membrane. And at first glance, it looks the same. So here we have this motor called kinesin, key 5B, I'm going to call it kinesin, which pushes filaments, which walks towards the plus end of the filament, so it pushes them in the opposite way, doesn't matter. And if I put enough of it, the filament will just move like this. I can put the motor that goes in the opposite direction, which is called NCD, and the filaments will be pushed by NCD only, and they will glide, and you can already see that these two motors have different gliding speeds because they're different motors. But anyway, if I put too much kinesin, you have kinesin gliding. If I put too much NCD, I get NCD-like gliding. If I mix them in the right concentration, the filament is stuck. It moves a bit depending on fluctuation, but it's not going anywhere. However, now, underneath all of this, the motors are moving. And because we can fluorescently label them, we can see where they are. And you will see that while the filament is stuck, the NCD will accumulate towards one of the ends, and the kinesin will accumulate at the other ends. And you can very clearly see this from the profile. The profiles are a bit different for technical details, but what you have here is a locally inhomogeneous concentration profile, which still leads to a tug-of-war condition, but it's moving underneath it. And again, this configuration in which we are taking magenta motors and bringing them here and cyan motors and bringing them here, it's a bit like a Maxwell demon that I described you about, with a big difference that now, and the following animation was very hard to do, so I hope you appreciate, if for some reason there are fluctuations in the relative number of motors, the Maxwell demon reacts to it by moving in the opposite direction. On average, it will not move, but every now and then it can shuffle a bit. So far, everything is simple, but let's see what happens when we increase the concentration of filaments a little bit. You start to see that even though we are in conditions where we would expect tug of war, the filaments are aligning a bit and moving a bit. And what is going on is that this inhomogeneity in the concentration of motors are being felt by neighboring filaments that react to it. Very schematically, you have two filaments oriented this way. Magenta motors will go inside which will create an accumulation of magenta motor inside here, which will push the two filaments apart from each other. And this is what you're seeing here, where this guy is pushed away just because locally the other one has accumulated too many motors that will push it away. And conversely, if your filaments are parallel, these magenta motors will accumulate here and push this other guy left. The cyan motors will accumulate here and push this other guy right, and you get this kind of bundling events. So while this is a very local concentration change, because you have this feedback between the fact that motors walk one way and the filament is pushed the other way, and because this accumulation in this condition is enough for this effect to be felt by neighbors, you get this. Now we increase the concentration even more, and if I have too much NCD, I think, you get gliding. Nothing special about it, is what I showed you at the beginning. If you have now too much kinesin, you get gliding. It's faster because now kinesin is the dominating motor. But if I put both of them at the same time, you get this. Parallel filaments align, anti-parallel filaments go away from each other. And this is everywhere on the whole sample, from micron scale to millimeter scale, and the system evolves into these bands of filaments which span large length scale and that don't move anymore. They are stuck this way for length scale and time scales much longer than the microscopic ones. And to really see what's going on, what we need to do is to look what the motors are doing, and this is what they're doing. The filaments are segregating into these bands, which separate domains enriched in kinesin, in magenta, from domains enriched in NCD, of NCD in cyan. So this reaction between local inhomogeneities and the motor's concentration evolves until you reach a new steady state, which is composed of these domains. And all the microtubules at the edge of these domains are polarized because these are continuously pumping cyan magenta motors inside and cyan motor outside. And it's starting to look a bit like this. This is the closest we will get to a real cell. But by just throwing everything together, we have self-organized a polarized architecture that it's able to sort motors in different domains. Just to make sure we really understand what's going on, you start from an homogeneous state. All the filaments are covered with roughly the same amount of the two kinds of motor. But because of transport, the motors will move, which will create locally an overaccumulation of, in this case, magenta motors. You need to imagine this is a periodic thing, so it goes on and on. This accumulation of motors will create a big force on the microtubules which move, and this is why you get this first expansion, until you get to a new state where all of these forces and motors concentration are balanced, and you end up in this new steady state, which, however, is continuously being fueled by motion of motors along the filaments. And very roughly, you get a steady state where the two concentrations on opposite domains are such that the mean force on the filaments at the interface are on average 0. And at the same time, you can have this if all the parameters are such that the diffusive flux of motors, which is still going on underneath, so the cyan motors don't like to be accumulated here, they would like to escape, but every time they try to escape, they're put back by the microtubules at the interface. So what you have is Maxwell demons continuously sorting and compensating diffusing fluxes in order to get this. A couple of experiments to convince you that everything I told you is right. The motors are still diffusing. This is a photobleaching experiment where you remove the intensity of the motors and they recover. The microtubules don't recover because nothing is regrowing the microtubules, but the motors are diffusing underneath all of this going on. This is an ablation experiment where we cut the microtubules at the edge, and you clearly see that the microtubules are under compression. So these motors were pushing this way. These motors were pushing this way. When we cut them, we unbalance the equilibrium. They go together in the end. And even more dramatically, this is a very delicate equilibrium. So now I'm going to show you another photoablation experiment where we completely destroy one edge of the pattern, and the pattern dissolves. Because all the motors that were trapped in here now can escape. All the motors that were prevented from going inside now can come. And these poor guys say, then I need to move, and they go away. Very quickly, this can be rationalized a bit. You just imagine you have microtubules in a periodic array. This will create the motor concentration profiles I told you about. We focus only in here. We have one microtubule, one motor that is moving on it, will go this way and exert a force the other way. But there's also another population of motor which is diffusing, and the two populations are coming and going with some rates. And using all of this, it's very simple. It's 1D drift diffusion equations, but still the solution has hyperbolic functions, which became a bit too complicated for me as an experimentalist. But you can still find the final equilibrium profile of motors in these conditions under the assumption that the filament is somewhere in the box, which fits reasonably well despite the simplicity to experimental data. And now you just use this profile to compute the total force that the motors are exerting on this microtubule, just the integral of the concentration, roughly. You then imagine you have an opposite population that is pushing the other way. You balance these two forces, and if there exists a position of the microtubule and all of the other parameters are such that such position where force balance is possible exists, this is your condition of existence for patterns. And the prediction of the model is that, those arrows, if you put too many of one motor, you get gliding. If you put too many of the other motors, you get gliding. And in between, you have a pattern space. And you can see that it only depends on the motor ratio and not on the absolute concentrations. And Bagianat did a lot of experiments checking that this is also true in experiments. So if you start with too much NCD, too much kinesin, you get gliding. As you decrease the relative kinesin concentration, you get patterns and then gliding again. And at the same kinesin concentration, you can have patterns or not, depending on whether the NCD concentration on the other side can compensate them or not. You can also see this pattern is non-symmetric, and this is because the two motors don't have the same speed. And this is also something that we can account in the theory. The precise position of this phase boundary will depend on the relative speeds and all of the other geometrical parameters of the model. And this is a system which is dynamic and responsive. It's not dead. It's continuously maintaining its state dynamically. This is another cool experiment. So we start with filaments gliding, and then Bagianat from the top is adding more and more motors of only one kind. So the system starts in the gliding phase, then motors arrive, now-ish, patterns form, and now new motors arrive, patterns dissolve. So you can dynamically close the phase boundary and make the system move. So it's not stuck in any arrested state, it's really a dynamically steady state. And the pattern size, another prediction, is that it will vary with the relative motor concentration, which is also something that we can test. And already you see that you don't have only gliding patterns gliding, but the patterns you get can be modulated. So this means that the cell can choose how to sort the motor just by varying locally the motor's concentration if you want to have this kind of approach to it. In how much time do I have? You're going to have to ask a lot of questions then. Because I just want you to focus your attention on a different way of seeing this. Now, when I was looking at this, and this is the advantage of being a physicist in a group of biologists, I was like, this looks like something, and this looks a bit like spinodal decomposition, like the phase separation of a binary mixture. You have two fluids, motors, and somehow, starting from an homogeneous state, you decompose into two phases, and microtubules, I call them Maxwell demons because it's a cool name, but are sort of acting like active surfactants, like going at the interface and maintaining it. And indeed, this begs for a Fourier transform. You start from an homogeneous state and you get a peak at density, which, despite the very poor quality of the data and of my Fourier transform, looks a bit like what you would expect for spinodal decomposition. So we went to Jean-François again and said, look, can you write me a theory that looks like this? And he said, yes, but you have to write it with me. And so what I'm going to tell you, I have partial control on, so be gentle. But basically, the idea that motors and microtubules can sort into supramolecular phase-separated patterns is around in the literature. There's a very nice paper by Erwin Frey very recently with a different system. But I think this is especially clean because you really have two populations that they mix. So what Jean-Francois came with, it's a free energy. It's really the stupidest thing you can do. It's the free energy of an ideal gas. We have free fields, microtubules, which have their own polarity, and two opposite motors populations. Everything is an ideal gas. You don't want to create interfaces. There is a bit of a splay term. And there are these sketchy terms that we can discuss because I think we have enough time, but I will let you ask about them. But very roughly, this is an ideal gas. And to this, you can extract equation of motions to which we just add two active currents, one which says if there is a microtubule, the motors move along its polarity. And the other one says if there is an asymmetry locally in the motor concentration, the microtubules will move either along or against their polarity, depending on what kind of motors they are. You take this, you simulate. This is binodal decomposition as far as an experimentalist can say that. And also the structure factor looks relatively close to what you would expect with a peak forming and then slowly shifting. And this model also captures a little bit more of the experimental data, and this is still very preliminary, so I don't really have a lot to show you. But these are the pattern size thing I was telling you about. We keep one motor concentration constant, and we increase the other one. Pattern size increases. You get from bicontinuous-like phases to, what's the word for gurke in English? I don't know. Cucumbers, thank you. And droplet-like things. And the model, as we vary the motor ratio, sort of recovers the results. And so I can start to summarize what I think we have. I'm going to flip the perspective a bit. So we started that we wanted to imitate cells, and we ended up with this. But now I think this is a bit of a deeper thing that we have here. So this is a class of models in which phase separation is driven by activity. In this model, there is no surface tension. These two gases of motors are not interacting at all. The only thing they do is they move on microtubules and push microtubules. So the only interaction they have is through active currents. So the shape and size of these domains, it's set solely by the fact that the diffusive flux has to be balanced by the microtubules at the interface, and that the force on the microtubules has to go to zero. So I think what we have here is just an experimental instance, an experimental example of a bigger class of models where activity leads to phase separation, which maybe has physiological implications in the group. We're working on it, and I am not in full control of that, so I won't tell you a lot about, but roughly, if you disrupt the architecture of the cell, and then you make it rebuild under certain conditions, you end up with something that looks a little bit like patterns of polarized filaments, indicating that maybe a process of this kind, not this precise thing, which is of course very idealized, but maybe a process of this kind is always in the background of the cells trying to maintain its polarized architecture. And with this, I am happy to take your questions.